This is the second mini-lecture for section 4.3. So far we've seen two different methods for finding the greatest common divisor. There's the method of intersection of sets, where we just list all of the divisors explicitly, and we take the largest thing that they have in common, or in other words, the largest element of their intersection. So that was the first method. The second was to use prime factorizations. The third method is rather different. It's interesting in that it does not involve really knowing very much about the divisibility of the two numbers at all. Okay, so I'm going to introduce it by going through this word problem. We're going to spell it out a little bit in more detail than we'll typically do on these problems, but I thought it'd be a good idea for you to see where this kind of reasoning comes from. Okay, the process, by the way, is known as the Euclidean algorithm because it was developed by the Greek mathematician Euclid in about 300 BC. Okay, and the example that I have here is very similar to the way he thought about it. So a company wishes to lay pipe in two straight lines. The first line is 84 feet long. The second is 186 feet long. Pipe comes in sections that are a whole number of feet long. What is the longest section length that can be used to lay both lines? So let's begin by measuring out the 186 feet with 84 feet. Yeah, suppose we use sections of length 84. Well, obviously, that wouldn't work for 186, but let's see how close we can get. Okay, so I'll just draw a little picture here. This is not supposed to be to scale. Okay, but we've got, 84 feet. Another 84. And then at the end, we have a little bit cut off. What is that? Well, this comes out to 168, which that means there's 18 feet left over. So we weren't quite able to do it with the 18 feet. With the 84 feet. But now let's try to do the 18 feet to measure the 84 feet. So now I'm trying to make the 84 with the 18. So here's 118. Again, not trying to make this to scale really. Okay, 2 18s brings us up to 36. Okay, another 18 brings us up to 54. And then another 18 is 72. And we didn't quite get there. We've got 12 left over. So we measured out the 84 with the 18s. And it didn't measure it out perfectly. There's 12 left over. Now let's use the 12 to measure out the 18. Okay, so we have a 12, and that didn't quite measure it out. We've got 6 chopped off at the end. Now let's try to measure out the 12 with the 6. And of course it measures it out perfectly. We don't have anything left over. So there's our 12. So let's think about what we've done here. 6 measures itself, of course, and it measures 12. Therefore, it must measure 18, since it measures both 12 and 6. Therefore, it must measure 84, since it measures both 12 and 18. Therefore, it has to measure 186, since it measures both 18 and 84. On the other hand, anything that measures both 186 and 84 would also have to measure this difference, 18. Therefore, it also have to measure this difference, 12. Therefore, it also have to measure this difference, 6. So, anything that measures both of these two numbers, 186 and 84, has to measure 6. 6 is the largest thing that measures itself. And 6 measures all this list of numbers. So therefore 6 is the greatest common divisor. So that last number we got in that process has to be the greatest common divisor. Okay, here's a faster way of doing it. Of course, usually you don't want to draw the pictures. Here's what we really did. We divided 186 by 84. Okay, that went in there twice. We had 18 left over. What we were really interested in here was the 18. Then we measured the 84 with the 18. In other words, we divided 84 by 18. That goes in there 4 times with the remainder of 12. So there's 12 left over. Then we divided 18 by 12. That went in there once. We have 6 left over. And then we divide 12 by 6. That went in there twice. And we had nothing left over. And we concluded that that last non-zero remainder was the greatest common divisor. So again, notice, each time, like, the new remainder becomes the next divisor. And the old divisor becomes the next dividend. Let's try this for another example. 840 and 490, which we just worked with a moment ago. So you should start by dividing the smaller number into the larger number. Okay, 490 goes into 840 once. And we get 350. Now I divide 350 into 490. It goes in there once. We get 140 left over. I divide 140 into 350. It goes in there twice. With 70 left over. And then I divide 70 into 140. And it goes in there twice evenly with nothing left over. So that means that this last non-zero remainder was the answer. Greatest common divisor of 840 and 490 is 70. Okay, just like we found a moment ago. But doing it this way, we didn't have to factor it. Sometimes numbers are not easy to factor. They're just big, and it takes a lot of guessing and checking. And so this is a method that would work with any pair of numbers, and it avoids having to do all that. Okay, so again, it's called the Euclidean algorithm, after the Greek mathematician Euclid, who's the first one who wrote it down about 2,300 years ago.